Explaining the seasons is one of those areas of confusion in astronomy. A lot of people think the seasons come about because the Earth is closer to the sun in the summertime and farther from the sun in the wintertime. And when you think about it, that doesn't really make sense because the difference between the closeness and the farness is only about 3%. And it seems unlikely that a 3% difference can cause the drastic differences that many parts of the world get in the seasons. The diagram right here shows a pretty good overview of that, and I'm going to break down each part of the diagram individually. But just looking at it holistically, in the upper left-hand corner you've got the Earth, and a lot of you maybe remembered in middle school that the Earth has a 23.5 degree tilt. That means that some parts of the Earth are angled towards the sun, and some parts of the Earth are angled away from the sun. The parts that are angled towards the sun aren't any closer. If you look, for example, the part in the northern hemisphere is angled towards the sun, and it's really not any closer to the sun than the similar latitude in the southern hemisphere. But the sun is much more closely overhead in the northern hemisphere in this representation than in the southern hemisphere. The big diagram, the bulk of this slide is taken up with the diagram of the Earth going around the sun. So it shows the Earth 4 seasons: summer on the far left, winter, northern hemisphere summer, I should say, on the far left, northern hemisphere winter on the far right, and then spring and fall in the foreground and background. This type of diagram actually is misleading because it looks like this Earth is really close for 2 seasons and really far away for 2 seasons, but that's because it's trying to show a side perspective. The lower left-hand corner shows the view from above. It shows the Earth's orbit nearly circular. The Earth, in that scale that's shown there in the lower left-hand corner, the Earth's orbit would be perfectly circular. And by the way, if the sun were that size, the Earth would be a speck, smaller in diameter than the line that represents the orbit. And here's just a zoom in of that. And there it shows the difference. At its closest, it's 147 million kilometers. At its farthest, 152. So that's a 5 million kilometer difference out of about 150. So it's 5/150ths is the difference between the closest and the farthest away. And there's the Earth again. By the way, the Earth's tilt changes a little bit over time, but having a stable tilt like that is really important for stability of life on Earth because that keeps the size of the tropics relatively constant. If the Earth's tilt changed quite a bit, that would really be difficult for a lot of living things, and certainly humans. We humans think that we're tough, but we're really pretty fragile. Here's a zoom in of the summertime. So notice in the summertime, so the summer solstice, roughly June 21st, the sun's rays are coming in almost straight overhead, actually straight overhead for some parts of the world. For our part of the world in Washington State, the sun's rays are never coming straight down. The sun is never straight overhead. But it does get to be more overhead. So if you think of a flashlight, if you were to hold a flashlight straight over a point on the paper, all of that light would be concentrated in just one circle. And that's what's represented by that diagram there. So the sun's rays are more intensely packed, they're more densely packed in the summertime. In the fall, the sun's rays are not densely packed and not loosely packed. So that's when we get roughly the same length day and night. In fact, equinox means equal day and night length. And on the spring and the autumn equinox, the day and night are almost exactly the same length. They're not quite the same. The equal night happens a little bit after the first day of fall and a little bit before the first day of spring, just a couple days in either case. Wintertime, so there again, northern hemisphere, the flashlight that in the summertime was like this, in the wintertime it's more like this. So the light is spread out over a greater area, which means that it's not going to be as warm. Wintertime, northern hemisphere winter corresponds to southern hemisphere summer. So that person that's standing in the southern hemisphere, they are getting the concentrated light again. And that is a pretty big difference. That 3% difference that we saw before, that isn't very meaningful. But this is a pretty big significance. And you can also, if you look at the size of the shadow, look at the size of the shadow of the northern hemisphere person. It's really short because the sun's rays are coming in fairly close to straight overhead. The southern hemisphere person, that shadow is fairly long because the sun is coming at more of an angle. That's reversed in the winter, the northern hemisphere winter. Now the northern hemisphere person's shadow is long and the southern hemisphere person's shadow is not very long. Here's a good summary of the path, the apparent path that the sun takes around the earth in the summer, first day of fall and spring, and the first day of winter and most of winter. So notice in summertime, a northern hemisphere summer, the sun rises north of east, gets to be high in the southern sky, and then sets north of west. So it's in the sky for a long time, and it's high overhead in the summer. Fall and spring, the sun rises pretty much due east, and in fact on the first day of spring, the first day of fall, the sun does rise due east. Gets to a mid elevation in the sky, a mid altitude in the sky, and then sets due west. And it's in the sky a mid-range amount of time. In the wintertime, the sun sets south or rises south of east, gets not very high in the sky, and sets south of west. So notice throughout the year the sun rises in the eastern part of the sky on the eastern part of the horizon, sets in the western part of the sky on the western part of the horizon, but only 2 days of a year does it rise due east and set due west. And if this was a static diagram, we would see that the person's shadow would be short at noontime, first day of summer, because the sun is close to straight overhead. And by the way, the latitude represented here is roughly Seattle's latitude, maybe a little bit farther north on this. Fall and spring, the shadow, it would be mid-length at noon. Wintertime, the shadow would be really long because the sun is low in the sky. This is another way to think of the seasons, the constellations that we see. So the constellations don't affect the climate on Earth, they don't affect the temperature, but the time of the year does affect which constellations that we see. So there are wintertime constellations and there are summertime constellations, and those are defined by the time of day that the constellation rises. So constellations that rise about when the sun is setting, they would be that season's constellations. So constellations that are rising in the summertime, approximately when the sun is setting, those would be summertime constellations. Constellations that are rising approximately when the sun is setting in the wintertime, those would be wintertime constellations. So if we take the two examples in the diagram, August 21st, if you are on Earth August 21st, you're looking at the sun, so the season is defined by the angle of the Earth's North Pole compared to the sun. So on August 21st, you would be looking at the sun. The sun would be, and not directly at the sun, of course, because that's dangerous, but if you were looking in the direction of the sun and you could somehow see the constellations during the day, the constellation of Leo would be behind it. Go over to February 21st. If you could look beyond the sun during the daytime, the constellation of Aquarius would be behind it. Now that might sound familiar to you if you know about the zodiac signs. The zodiac sign of Leo corresponds to around that time in August. The constellation or the zodiac sign Aquarius corresponds to that time in February. Interestingly enough, for Leo, you can't see the constellation Leo during the time that you would read your horoscope for Leo, which is the end of July to the end of August, because the sun is in line with Leo. So Leo would not be an August, that would not be a late summer, early fall constellation, because Leo can't be seen August 21st because it's in line with the sun, and the sun is illuminating the atmosphere, which is keeping us from seeing the constellations near us. So the best time to see Leo would be 6 months later, or 6 months earlier, February 21st. Best time to see Aquarius isn't February 21st because the sun is in line with Aquarius then. Best time to see Aquarius would be 6 months later, or August 21st. And the same pattern holds true for all of the constellations. Again, that doesn't relate to the seasons and how they affect the Earth, but that does affect the seasonal constellations. So thank you for watching that, and I hope that gives you a decent understanding here of how the seasons work and then how the constellations tie in with when you can see them and the seasons.